Question 8 from the 2019 Advanced Higher Physics SQA exam. Muons are created when cosmic rays enter the atmosphere of the Earth. This is shown in figure A, shown there. It's not drawn to scale. Now, to an observer on the Earth, the muons appear to have a lifetime of 8.5 microseconds. Instruments on Earth can detect muons and measure muon energy E. The precision of the muon energy measurement is limited by the lifetime delta T of the muon. And for 3 marks, we're asked to, by considering the Heisenberg uncertainty principle, calculate the minimum uncertainty in the muon energy delta E. Well, we go to our data sheet, and I think we can identify the 2 equations dealing with Heisenberg's uncertainty principle. The top one is to do with the uncertainty principle in relation to the position of the particle and its momentum. So it's the second one we're going to be looking at. Delta E times delta T is greater than or equal to h divided by 4 pi, which means that multiply those 2 values together, that must be the basic minimum value. So we're after the delta E in this particular case, so let's go and do the calculation. We can write down the equation, delta E and times delta T is going to equal to h divided by 4 pi. Now we've got to rearrange because we want to find delta E. So delta E, if we rearrange, divide both sides by delta T, we have h all over 4 pi, and we have to divide that by delta T. So there's our equation there. We can easily plug in the numbers now and find out the value of delta E. So delta E is going to be equal to, and you'd have to look up your data sheet for Planck's constant, and we know that Planck's constant is going to give you a value of 6.63 times 10 to the minus 34, and that's going to be joule seconds. And when we divide that by 4 times pi, so 4 times pi, I'm going to be multiplying that by delta T, and delta T in the question is 8.5 microseconds, so 8.5 times 10 to the minus 6 and seconds. And you can see the 2 seconds cancel out, and we're left with an energy delta E in the units of joules. So if we do that in our calculator, the uncertainty in the energy comes out to be 6.20 times 10 to the minus 30 joules. You get your 3 marks. Question 8 continued, part B. Some muons detected at sea level have an average energy of 4.1 times 10 to the power 9 electron volts, eV. An instrument detects 10,000 such muons in 1 minute. And for 3 marks, we have to determine the average total energy in joules measured per second. Now the key to this problem is you know that 1 electron volt really is 1.6 times 10 to the minus 19 joules. 1 electron volt is the standard unit of measurement for the particle physicists when they're dealing with energy. Where did it come from? Well, we know that when an electron of charge 1.6 times 10 to the minus 19 coulombs passes through a potential difference of 1 volt, it will gain energy of the value of QV. So we multiply 1.6 times 10 to the minus 19 coulombs by 1 volt, and we'll get what 1 electron volt is. It's that up there, 1.6 times 10 to the minus 19 joules. So now we know the unit of energy for the electron volt. We now can do our calculation based on 1 minute. So we put down 1 minute, and we can find the total energy which arrives. It's going to be equal to 10,000 times the average energy of one of those muons, so 4.1 times 10 to the power 9 electron volts, and we've got to multiply that by, remember, what 1 electron volt is, 1.6 times 10 to the minus 19, and that's going to be joules per electron volt. So you can see the 2 electron volts are going to cancel out, and we're going to be left with the energy which is going to be arriving there in 1 minute. And if we do that in a calculation, we get energy is going to give you a value of 6.56 on your calculator times 10 to the minus 6 joules, so minus 6 joules. And remember, this is per minute. But we're asked to find the answer in per second, so the energy would be equal to this number here, 6.56 times 10 to minus 6 joules, and we have to divide by 60 seconds because there are 60 seconds in 1 minute, and we end up with 1.09 times 10 to the minus 7 joules per second. So that's the answer for 8B. Question 8C. At sea level, these muons have an average momentum of 4.87 times 10 to minus 19 kilogram meter per second. By calculating the de Broglie wavelength of a muon with this momentum, explain why muons at sea level can be regarded as particles. Well, they'll be regarded as particles if they don't show up any, we can't see any wave interference or wave diffraction or wave phenomena as it's called. So we don't see any wave phenomena, we then will regard the muon as a particle. So let's take a look at the actual wavelength of the particle, the muon, with this momentum, and we can find that from our data sheet with the equations. You can see the second equation down is the formula for de Broglie's wave. Lambda equals h divided by p, where h is Planck's constant and p is the momentum. So let's calculate the de Broglie wavelength for these muons, and if we put down our formula, lambda is going to equal to h divided by p, and we know that h is going to be Planck's constant, which is going to be 6.63 times 10 to the minus 34, and the units for Planck's constant are joule seconds. We're going to divide that by the momentum, and the momentum is 4.87 times 10 to minus 19, and you've got a big unit of momentum here, kilogram meters per second. So leaving aside the units now and saying, well, they must work out to give us a wavelength in terms of meters, on our calculators, lambda works out to be a value of 1.36, and it's going to be multiplied by 10 times 10 to minus 15, so it's minus 15 meters. So that's the wavelength of these, the Broglie wavelength of these muons. Now, as you can see, the wavelength of these muons is much smaller than the atom dimension of the atom. If we think of a typical atom, its dimensions is the order of 10 to minus 10 of a meter. So you can see the Broglie wavelength for a muon is 5 orders of magnitude smaller than the size of the atom. Now, in order to see diffraction effects or wave effects, you have to have the width of the barrier much smaller than the wavelength. And if it's going to be the wavelength of these de Broglie waves is going to be of the order of 10 to minus 15 meters, and considering an atom is 10 to minus 10 meters, then we're not going to see any wave phenomena from the de Broglie waves of a muon. Definitely not. So therefore, at that particular level, we can consider the de Broglie wave to be a particle. Now, just some other talk about the units here, because I think it's very important to see that these equations work with units. The units for lambda, we worked out in a calculation were joule seconds divided by kilogram meters per second. Now, if we take that second down to the bottom line, we have joules divided by kg, kilogram, and it becomes meters per second per second. Now, that's going to be an acceleration. So we have mass times acceleration, which really is a force, which is newtons. So the unit then boils down to joules divided by a newton. But we do know that the joule is unit for energy, and energy can be written in terms of work done equals force times distance. So the force would be newton, and it would be a meter, and divided by a newton, and you can see the 2 newtons cancel and you're left with a meter. So that means our formula lambda equals h divided by p does give you the value for length, which is the wavelength in this case. So 1.36 times 10 minus 15 meters. You're not going to see diffraction effects or wave phenomena because the size of the wavelength is much smaller than the size of the atom.